Hello, welcome to our talk. My name is Kylie,
My name is Sam.
and our project was studying the dynamics of a Vibro-Impact energy harvester system. And we did this work in the summer of 2020 at Georgia Tech with Dr. Kusk and Dr. Serdikova.
Okay, so the setup for the model is, first of all, the reason why people are interested in this is because it's a potential renewable energy source. So the way it's set up is you have a capsule, and on both ends of the capsule, you have some polymer. And you have a ball inside where you apply some sort of force, some sort of forcing function, F, to the capsule, which moves the ball, and the ball will hit the ends of the capsule and deform the polymer. And this deformation will turn into electric energy that you can then use. So it converts kinetic energy into potential energy. So that's how the harvester works mechanically.
Yep, and there are a bunch of parameters of this harvester that we care about. So you have capital M, which is the mass of the capsule. You have lowercase m, which is the mass of the ball. We care about things like the length of the capsule, the angle of inclination. So you can see that the capsule is kind of slanted a bit and forced along that angle. So that angle is beta. We have the coefficient of restitution for the elastic polymer at the bottom end of the capsule. So we call that RB. And then again, for the elastomer at the top end of the capsule, which is RT. And then we also care about the amplitude and frequency of the forcing. And an important parameter to keep track of is D, which is here m omega squared over a pi squared times S. And D is kind of just a new parameter that we introduced to kind of keep account or keep track of a lot of parameters in our equations without making it too messy.
Okay, so the restitution coefficients are the parameter that another parameter that we really kept a close eye on to see how it affects the dynamics of the system. So the case where you have a restitution coefficient where your energy return is the same for both ends of the capsule was studied by our mentors, Kusk and Serdikova. And so what Kylie and I worked on is we consider the case when the energy return on the top of the capsule and the bottom of the capsule aren't the same. So we introduce some sort of asymmetry into the system. And this model is first off a bit more realistic, right? In reality, you never have completely symmetric restitution coefficients for the capsule. And we were really just interested in, okay, well, what sort of behavior is this going to produce, right? And we also wanted to get some analytical results and use these alongside some numerical results to just observe the behavior and hopefully, outside of just observing the behavior, also maybe be able to draw some conclusions about the energy output and what type of coefficients are best for the energy output.
Yep. So one way we started understanding the types of motion are looking at these two types of graphs. And so here we see four different types of motion: asymmetric, symmetric, chaotic pre-grazing, and 2-1 post-grazing. So let's go through each of them and see what's going on. So the top row of graphs, these are all phase planes with the relative velocity of the ball and capsule on the y-axis and their relative positions on the x-axis. And then in these bottom graphs, you see the like blue sinusoidal thing is tracking the top of the capsule. The red sinusoid at the bottom is tracking the bottom of the capsule. And then that sawtooth zigzag is the motion of the ball. So kind of when that zigzag hits the top sinusoid, that's hitting the top of the capsule, and likewise for the bottom. So one type of motion we can get is this asymmetric motion. And so in the phase plane, you can imagine the ball starts on the left side, it's, rolling across the top to hit the right side, and then it kind of hits and then goes back. And so that motion kind of hitting each side is hitting the top and bottom, and then it has, some sort of motion in between. So there's, an asymmetric possibility, which is what we often see. But you can actually tweak parameters, whether that's restitution coefficients or the length or other parameters in the system, and you can get more symmetric motion, which is what you see in the second column. We can also get some pretty chaotic motion, as you can see in this third column, where kind of every cycle of impact top and bottom isn't quite what it was before. It's not very consistent. And in this case, actually, you can see in that bottom, after that bottom impact, it's kind of getting closer and closer to hitting the bottom again, right? It gets really, really close to hitting the bottom end twice. You see that kind of knot forming in the top graph, and then in the bottom, the sawtooth part kind of gets really close to the red sinusoid. And so once that gets like really, really close, it kind of almost grazes the bottom of the capsule again. That's called grazing. And then right after grazing happens, we actually get 2-1 motion, which is really interesting. So instead of the ball bouncing between the top end and the bottom end, bottom, top, bottom, top, bottom, top, it'll actually hit the bottom of the capsule twice. That's what you see where that knot kind of intersects that end. So it'll go bottom, bottom, top, bottom, bottom, top is the kind of the impacts that we'll be seeing. So those are all different kinds of motion that we observed right off the bat.
Okay, so now that we've gone over what these different types of motion are, we want to know what effect they're going to have on the energy output. So just to start off on the right, the graph on the right is the average energy output, and the graph on the left is plotting the relative velocity against that parameter value we mentioned, d. So what we see is for varying values of d, the energy is pretty consistently decreasing for the most part until we hit grazing at, it's approximately 0.2, right, is where we hit grazing. And then we get this big drop in your average energy output. A significant drop in your average energy output. And right, you can see where this occurs on the left, right around 0.2 once again, where when grazing occurs right here, there is an additional impact, a very low velocity impact that is added to the system. And what we were curious about is, and the next natural question to ask is, can we shift this somehow? So, okay, grazing, we're going to get worse energy output. Is there a way to maybe just move this a little bit to the left, or maybe we can move it a little bit to the right as we please?
And so that's where playing with changing the restitution coefficients on the top and bottom, being able to do those independently of one another came in. So here you can see each column are just 4 different combinations that we picked somewhat randomly to just see what happens as we tune the top and bottom restitution coefficients. So the second column, you can see that's the case where the top and bottom restitution coefficients are the same as one another. So that was kind of our baseline. That's what had been studied. And in the 3 other columns, you can see compared to that, when you change the top and bottom restitution coefficient and make them not equal to one another, how does that shift the parameter of D at which that big drop happens due to grazing? So if we say that in the symmetric case, in that second column, we can estimate that that happens maybe slightly after D is 0.2, let's say D is 0.21 or something. We can see in the third column, for example, if you decrease the top restitution coefficient a bit and increase the bottom restitution coefficient a bit, you can shift that drop to the left, right? That's now happening for a smaller D value, maybe D is 0.8 or something like that. And if you, maybe pick another set of parameter values just to see what happens, if you make the top restitution coefficient 0.4 and the bottom one 0.6, like in this fourth column, oh my gosh, what happens? It actually shifts that, but now to the right, right? This drop at D is now maybe happening at D is 0.23. So that was kind of our first experiment to see if we could shift the parameter of D at which this drop is happening by changing the top and bottom restitution coefficients.
Okay, so like Kailee mentioned, those were sort of our first experiments to see just what impact changing the restitution coefficients would have, and we picked the restitution coefficients for the top and bottom somewhat haphazardly, just trying things out. So in front of you, you have these heat maps where on one axis you have the ratio between the coefficient of restitution on the bottom and the coefficient of restitution on the top, right? You have their ratio for a wide range of values. So these graphs include a lot of information about the behavior for different coefficients. And so just to explain what these are first, these heat maps, the heat in this case is energy output. So the redder areas are going to be higher energy output. And you'll notice all these red dots and black diamonds in the graphs as well. And those are transitions in the type of motion. So up here, for a corresponding value of D and a ratio, you have just 1-1 motion, just back and forth, back and forth, back and forth. And let's say we're going down, we're changing D, and then we have period doubling. So still just 1-1 motion, but the period has changed. And then if we keep going down, okay, and then we'll have a transition to 2-1 motion, right? So we'll get that additional impact on the bottom. So now we have 2 impacts on the bottom, 1 on the top. And we can see for everything below that, right, energy output is generally speaking quite bad. But some takeaways from this is first off, for these ones on top, this D value, which which is here in the slides, that's being changed by increasing S. So that's how we change D in these top 2 graphs. And we see that for larger values of D, which means larger values of S, we have a wide range of stable motion, stable 1-1 motion with high energy output. So bigger values of D, longer lengths of the capsule, any RB RT ratio you have is resulting in nice stable 1-1 motion with good average energy output. Down here on the bottom, a takeaway, and in this case, we're changing D again, but in this time, we're changing A, the amplitude of the forcing that we're applying to the capsule. So we're changing this A. So as A increases, and thus as D decreases, we generally have higher energy output. Something else to observe here and to maybe note is the ratio for RBRT that seems to work. In this case, right, I noted it's about 1.3. So the capsule is at an angle of some sort, and this makes the velocity not quite equal. It adds some asymmetry because you have the force of gravity pulling the ball down, whereas going up, it's fighting against the force of gravity. So there's some asymmetry there where on the way down, let's say the velocity is a bit quicker. If you choose a slightly bigger bottom coefficient than top, which will make the motion slightly more symmetric and sort of counteracts the effect of that incline. That's typically where you get the best energy output, generally speaking.
Yep. So those were a lot of our numerical results, but as we said at the beginning, we wanted to study both numerics and the analytical results. So how we studied these analytically is we considered two maps. Path 1 or P1 is what happens from when the ball hits the bottom of the capsule and as it's traveling up to the top. And then the path 2 or P2 is what's happening once the ball, is at the top and is traveling down to the bottom. And we study path 1 and path 2 with these big scary equations, which are not important to this talk, but some parameters of kind of like making a bit of sense of it basically is z dot is the relative velocity between the capsule and the ball. So, you're kind of understanding like, where is the ball within the capsule and like, how is it moving? And then you can see in P1, for example, right, we've got RBs in both equations. And RB, remember, is the restitution coefficient of the bottom elastomer. So that makes sense because in path 1, when it's moving from the bottom to the top of the capsule, it just hit the bottom, it just bounced off. So that's why RB is going to be important. And exactly analogously for P2, RT, right, it just hit the top of the capsule, it just bounced off the top of polymer. And so it's, that coefficient is going to be important and it's moving down. So those are the two equations and they're scary, but they were really useful in helping us learn a lot more about the system.
So yeah, and so one place where those equations will hopefully be useful and are useful is bistability. So bistability is when a system has two equilibrium. So what does that mean? Well, where you can see this is this graph of the relative velocity at the kth impact versus just the ratio of our BRT. If we look at, let's say 1.2, you'll notice there's two possible options, right? There's two branches that you can follow. You can either follow this one on top, or there's also one on the bottom that you can follow, right, at about 1.2. And so this is an interesting dynamic behavior that we observed. But I mean, there's a lot more to be explored here. So first off, given an initial condition, so I just say, okay, your initial velocity is this. Which branch is your solution going to follow, right? Which is more likely to be followed? Which of the two equilibrium is more likely to be followed? And a good basis for this would be the analytical results that were derived. That would be a good place to start looking for this. And then also, right, the question we're most interested in is what impact does this have on the energy output? So, right, so one of these branches will correspond to better energy output, and we're definitely also interested in that. But yeah.
So in summary, we've reached the end and we learned a lot. So we explored what happens when you use asymmetrical restitution coefficients as opposed to the two being equal to one another. And we saw that we can kind of tune the parameters to cause a shift in grazing and almost control where that shift happens. And the advantage of that is then we can create a larger range of values where we see the 1-1 periodic solution. And that's exciting because that has generally corresponded with a higher average energy output, which is ultimately what we care about in this energy harvesting system. Something that was surprising was that, even reducing a restitution coefficient could result in a higher energy output. So I don't know, maybe originally would have guessed that you want to increase the restitution coefficient. So you're getting the most energy out of every bounce off the end of the capsule. But given the overall dynamics of the capsule, that's not always the case. So that was really interesting. And we saw that this can cause really complicated things to happen, like bistability, and definitely raised a lot of questions that we would like to keep exploring.
Okay, so thank everyone for listening and watching, and we would also like to thank our mentors who were a huge help, and also the Georgia Tech School of Mathematics. So thank you, and we hope you have a good day.